Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to AC circuits. Previously we have covered AC circuits with pure resistance and AC circuits with pure inductance. Okay. So in this video we are going to discuss AC circuit with pure capacitance or only capacitance. Now let us say we have a circuit with a capacitor C connected to an alternating voltage source. So here the plates of the capacitor, they are charged first in one direction and then in the opposite direction depending upon the. So here with the charging of the capacitor in alternate directions, it results in the flow of an alternating current. Okay, this. Now here we have to figure out what is the expression of the alternating current. So we know in a capacitor, the capacitance is given by the charge in the capacitor and the voltage applied across the capacitor. So here if we apply KVL, if the voltage across the capacitor is Vc, then Vt, which is the applied voltage, minus Vc, that is equal to 0. That implies Vt is equal to Vc, or which is also a time varying voltage, so Vct. So here for this capacitor here capacitance is equal to Qt by Vt. That implies, so here we can write Qt is equal to CVt. Okay, now Vt here we can express as the time varying applied voltage, sinusoidal voltage, as Vmax sine omega t. Okay, so here we'll substitute the same, so this becomes C Vmax sine omega t. Now we know current is rate of flow of charge, derivative of charge with respect to time. So here this is the time varying charge, so that implies current IT is equal to dQt by dt, derivative of charge with respect to time, which is equal to d by dt of C V max sine omega t. So that implies current is equal to C V max omega cos omega t, or we can write it as C omega or omega C V max sine omega t sine omega t plus pi by 2. We can write it in this way, sine pi by 2 plus omega t, that is cos omega t. So this here is the expression of current. We can write it now here like this. pay attention carefully. I am writing here it as IT is equal to V max by 1 by omega c sine omega t plus pi by 2. So here this 1 by omega c, it is called as capacitive reactance. Okay, 1 by omega c, that is called as capacitive reactance, which is also equal to 1 by 2 pi fc. Same thing. So this is called as capacitive reactance and its unit is in ohms. Okay, now this is in the general form. There is also a complex notation in terms of complex numbers, the imaginary numbers. Capacitive reactance is written as Xc is equal to 1 by j omega c. So when we multiply j on both the numerator and denominator, this becomes j by j square omega c or minus j by omega c. Okay, this is in terms of complex numbers. So in inductors, if you remember, the inductive reactance, it was XL is equal to omega L, or in terms of complex notations, j omega L. Here capacitive reactance is 1 by omega c or 1 by j omega c or minus j by omega c. So here we can write it as we can write IT as I max sine omega t plus pi by 2. Okay, this. So if we compare it with the voltage expression where Vt is equal to V max sine omega t, then here current leads voltage by pi by 2 radian or 90 degree. So here current leads the voltage current leads voltage by pi by 2 radian or 90 degree, or we can say voltage lags behind current by pi by 2 radian or 90 degree. So either way it is the same thing. And here I max is equal to V max by 1 by omega c or V max by Xc, capacitive reactance. This. Okay, so this is the expression of current. So from this expression we see that here current is leading the voltage by pi by 2 radian or 90 degree. So if we see the waveforms here, so this is the circuit consisting of a capacitor connected to an alternating voltage. This is the waveform. Okay, so here the black AC waveform, it represents voltage, and the red waveform, it represents this circuit current. So here if you see as we found out from the expression, current leads voltage by pi by 2 radian or 90 degree. So here there is a difference of pi by 2 from the starting 0 points of current and voltage. So current is leading the voltage by pi by 2 radian or 90 degree, or we can say voltage lags behind the current by pi by 2 radian or 90 degree. And similarly, there is a difference of pi by 2 radians between the corresponding 0 points and the corresponding positive peaks and negative peaks also. Same pi by 2 radian or 90 degree phase difference between the 0 points and the positive and negative peaks. So from this waveform we get to know that current leads the voltage by pi by 2 radian or 90 degree, or voltage lags behind the current by pi by 2 radian or 90 degree. Now for the phasor diagram, there are two ways in which we can express it. First, first consider the right hand side. We take Vrms as reference. So this diagram, it represents current leading voltage by pi by 2 radian. This. Current leads voltage by pi by 2 radian or 90 degree with Vrms as the reference phasor. This here represents with Irms as the reference, here it represents voltage lagging behind the current by pi by 2 radian or 90 degree. Okay, voltage lagging behind the current by pi by 2 radian or 90 degree. Okay, so both the phasor diagrams, they essentially convey the same information, just there is a difference between the reference phasors. So either you say current leads the voltage by pi by 2 radian or voltage lags behind the current by pi by 2 radian, it is the same thing. Okay, so next is the concept of instantaneous power absorbed by the capacitive circuit. Okay, instantaneous power PT. So here instantaneous power is simply the product of the instantaneous voltage and current. So it is Vmax sine omega t, which is instantaneous voltage, multiplied with the instantaneous current Imax sine omega t plus pi by 2. So we can write it as Vmax sine omega t into Imax cos omega t. Okay, Vmax sine omega t or Imax cos omega t. Okay, this. So here it will be equal to Vmax Imax sine omega t cos omega t. Here multiplying and dividing 2, here and here also 2, we get Vmax Imax by 2 here it is sine 2 omega t. Similar thing we did in inductance case also. So this is the expression of instantaneous power. So here we have this 2 sin x into cos x is equal to sin 2x. This trigonometric identity we have used. Now if we want to find out the average power over one complete cycle, then we have to integrate the instantaneous power over one complete cycle. So that will be equal to the average power so P average is equal to 1 by T 0 to T Pt Dt, which is equal to 1 by T 0 to T Vmax Imax by 2 sin 2 omega t dt, which is equal to Vmax Imax by 2t, taking it outside, the integration 0 to t sin 2 omega t dt. So I'm writing it in this side. So it is Vmax Imax by 2t integration of sin 2 omega t dt, it will be into 1 by 2 omega minus cos 2 omega t from upper limit capital T to 0. Integration of sine is equal to minus cos, and here we are integrating with respect to t, so 2 omega it behaves as a constant, so this is the expression. So this becomes Vmax Imax by 4 omega t, taking minus outside also, here it is cos 2 omega t minus cos 0. Okay, we have taken minus sign also outside. Now same thing which we did in the inductance case also, omega is equal to 2 pi by t, where t is the time period. That implies omega t is equal to 2 pi. So here it will become cos 2 into 2 pi, so this will become cos 4 pi, and this will become cos 0 as it is, cos 4 pi minus 0. So this will be equal to 1 minus 1, which is equal to 0. So this multiplied with 0, this whole thing, the result will be 0. The average power is equal to 0. So it is similar to the average power in a circuit. Sorry. So it is the same as the average power in a circuit with pure inductance. The average power in pure capacitance is also 0. Same in inductance and capacitance. The average power is 0 over one complete cycle. Now, if we want to draw the power curve, it will be something like this. Here, this is the power curve. If you remember, this is the voltage and current waveform diagrams. This is with the power curve along with it. So this blue one, it represents the power. Okay, the blue one represents the power curve. Black one voltage, red one current, blue one power curve. So here also we'll do the same thing. We'll divide the entire thing from 0 to 2 pi into pi by 2 radians segments. Okay, so if here you see from 0 to pi by 2 on the omega t axis, here if you see, you will find from 0 to pi by 2 current is positive in the upward direction, voltage is positive, power is product of voltage and current, power positive into positive will be positive, so power is also positive. It has a positive peak, it is in the upward direction, the waveform is in the upward direction. Okay, so from 0 to pi by 2, voltage positive, current positive, power product of voltage and current positive into positive, that is also positive. Then from pi by 2 to pi, here from pi by 2 to pi, voltage is positive. Okay, voltage is positive, but current is negative. Okay, current is negative, the red one. So positive into negative, product of voltage and current, it results in a negative power. So it is in the negative direction. Negative. The power waveform is in the downward direction from pi by 2 to pi. So from pi by 2 to pi, voltage is positive, current is negative, so power positive into negative, that is negative. Okay, then from pi to 3 pi by 2, from pi to 3 pi by 2, here the current, the red portion from pi to 3 pi by 2, the current is negative and also the voltage, the black curve from pi to 3 pi by 2, the black one is also negative, the black curve which is the voltage. So voltage and current curves both are negative from pi to 3 pi by 2. So negative into negative is positive. So that's why the power curve waveform is in the positive direction, the upward direction. So it is positive. So from pi to 3 pi by 2, voltage is negative, current is negative, power negative into negative, it is positive. Then from 3 pi by 2 to 2 pi, here from 3 pi by 2 to 2 pi, the current, red one, it is positive. Current is positive and the voltage curve, the black one, it is negative. So positive into negative, power, it will be negative. So the power waveform from 3 pi by 2 to 2 pi, it is negative in the downward direction. So here voltage is negative, current is positive, negative into positive, power is negative. So this is the nature of the power curve with average value is equal to 0. This, the average of the power curve during the entire cycle from 0 to 2 pi, that is equal to 0. Same as in inductance. Okay, so here we have discussed the basic concepts related to AC circuits with pure capacitance. Okay, from starting with the basic representation of voltage and current, their expressions, and then with the waveforms, phasor diagrams, power curves relating to instantaneous power and average power, then capacitive reactance along with their complex representations. So this is the